So that means if it is a point, so we can consider one line like this, and this angle is almost, it is like theta, and also the same angle is making here, that is also theta. Okay. So basically this tension and this tension are not exactly the same. Although it is acting on a point and this tension should be same, but it has a distance parameter, small distance delta x. So for that reason, you can say that this tension here at this point. So this is the tension at a point x plus delta x. So this is tension, same tension, but it has a directional parameter. That means it is working at x plus delta x, and this tension is at a distance x. That means this tension is not only T, it is T at a distance x. So this is T at a distance x. This one is the y-axis. So this is the thing. Now this tension x plus delta x, so this tension has a component in upward direction. So we can say this is T of this thing along upward direction. So this is T cos theta, this is T sin theta. So this we can say T x plus delta x sin theta, and this tension at a distance x, so this is also having a component along this, but we do not want this horizontal component, we only require this vertical downward component. So this downward component is Tx, and this is also sin theta. So we have one component upward and one component downward. So one is T x plus delta x, is upward, sin theta component upward, and one is downward. So this resultant difference of tension is producing an acceleration to this much of this mass of the string. Now what will be the mass of the string? So mass of the string, if we take mass per unit length of the string is equal to mu, then what we can say, that tension at a distance x plus delta x sin theta minus tension at a distance x. So this is equal to ma. Now what is this m? M is mass of this portion, and a is the acceleration of that small portion but along y. So acceleration of this small portion m, but it is along y. Okay. Now what we can do, that as because theta is very small, so we can write this sin theta as tan theta. So we can write T x plus delta x, and this is tan theta, and this is T at x tan theta, equal to, now mass of this small portion. What will be the mass of this small portion? So mass of this small portion will be mass per unit length into delta x. As because its length is delta x, so this portion has a mass mu delta x, and acceleration along y, so this is this one. Okay. So basically this is the classical form for finding the differential equation of a wave, transverse wave, or you can say any kind of wave must follow this equation. So if I write this equation here, so we can see, we can take common tan theta. So tan theta, let us take common tan theta. So it becomes tension at a distance x plus delta x minus tension at a distance x. So that is equal to mu delta x and acceleration along y. So acceleration along y can be written as, so this is basically del square y by dt square. So this is basically acceleration along y direction. That this tan theta can be written as del y by del x, and this tension is x plus delta x and minus tension at a distance x. Okay. And this is equal to mu delta x del square y by del t square. Now you see, we consider tension is constant. Basically we want to consider that this tension is a constant, because although the string has mass, but we have to consider that this tension is constant throughout the string. Now how can it be possible that a string that is having some mass have equal tension everywhere? So this is not possible. So what we have to do, we have to take common this tension out and make this dy by dx inside. So what it will give, that if we take this tension out, so we will get del y by del x at x plus delta x. That means the change in tension we are taking here, that change in tension is taking place due to the displacement of x. But tension is constant, it is taking place only due to the slope change. It is only taking place that different tensions at different portion is due to only the change in x or change in gradient, change in del y by del x, because tension is constant. So if this is the case, so we can take t outside. So the tension is constant, but the slope is changing. Del y by del x is changing. So that's why the tension variation can be seen. Okay. So we are considering tension as a constant. So del y by del x at x plus del x minus, this will be del y by del x at a distance x. So this is equal to mu delta x del square y by del t square. Okay, now see this thing. So if someone says limit delta x tends to 0, function of x plus delta x minus function of x divided by delta x. So we know that this is equal to basically f dash x from first principle, or we can say if f is a function of y, so this will be del y by del x basically, isn't it? So this will be the case. Now here what we are getting, so in place of f we now have del y by del x, and also here we have del y by del x. So good result. So the slope del y by del x at a distance x plus delta x minus the slope at a distance x divided by delta x. If we take this thing, so this should be equal to del square y by del x square, because this is like a function and it is again having a parameter at a distance x plus delta x. This is the slope at a distance, this is the slope at a slightly less distance, divided by delta x, where delta x tends to 0. So this will give you this thing. Okay, but here we do not have, see, we do not have this divided by delta x. So what can we do? So we can write this thing as t, so del y by del x. Okay, we do not have a divided by delta x here, so let us multiply a delta x here, and we can write this x plus delta x minus at a distance x divided by delta x. Now we have multiplied with delta x, so no problem. So this is equal to mu delta x and del square y by del t square. Okay. So up to this, now see, now this total thing. So by default it is delta x tends to 0. So this is the slope at a distance x plus delta x minus slope. So this will give you del square y by del x square. What you can write, this is tension delta x and this thing is del square y by del x square equal to mu delta x into del square y by del t square. So delta x is getting cancelled. So del square y by del x square is equal to mu by t del square y by del t square. In a string, the velocity of wave, transverse wave in a string, velocity of wave in a string is given by v equal to root under tension by mass per unit length. So this parameter mu by t, so mu by t is basically nothing but 1 by v square, 1 by velocity square. So we can write this equation as del square y by del x square equal to 1 by v square into del square y by del t square. So this is the classical differential equation of any sort of wave that has to be within this parameter. So it may be the wave in a string, or it may be electromagnetic wave, it may be any sort of transverse wave, even the approach for matter wave, for say electron. So first we have to consider like in this fashion, such that it maintains this differential equation. Then it will be called a wave. Okay. So this is the first part.